I will make a brief introduction of Professor Han. So Dongsu Han is currently a professor at the School of Electronic Engineering and Graduate School of AI at KAIST. He received his PhD in computer science from CMU in 2012. His research focuses on democratizing AI systems and addressing challenges in modern internet applications running on cloud infrastructure at scale. His current work encompasses AI systems for accessible large-scale model training and AI-enhanced video delivery. Throughout his career, he has published extensively in premier venues including CCOM, OSDI, NSDI, CCS, MOBISys, and ULSys. His contributions have been recognized with the NSDI Best Paper Award and the NSDI Community Award. He currently serves as an associate editor for TON and previously served as the PC chair for KAIST 2020. His current system work on ESMOE, which is published in ICM 2024, and Stellitron, published in CCOM 2024, represents significant advances in making AI training accessible using commodity hardware, where his ongoing research continues to push the boundaries of cost-effective AI inference on the edge. So today, the title of Professor Han's talk is Democratizing deep learning training towards training LLMs using consumer-grade GPUs. Yeah, give the time to Dongsu. Yeah.
Thank you for the introduction, and thank you for showing up early in the morning. I didn't realize my talk starts at 8:30, which is slightly earlier than normal talks. Okay, so today I want to share my experience on using consumer-grade GPUs in training and inferencing large language models. So we know that today's deep learning infrastructure is very expensive. Okay, we rely on expensive hardware that is designed for high performance. So after having spent a few decades on enabling cloud computing, we're now back to HPC, right? So this is ridiculous. They spend a large amount of money. All the big techs believe that AI will save the world. So it's so important that any money that they invest in AI is justified, right? So they're buying all these expensive hardware, housing them in data centers. And I would say that the key figure behind this industry is Jensen Huang, shown in the tiny space there, right? But a lot of us, academics, don't have access to these expensive resources. Instead, we often rely on consumer-grade GPUs, that is the RTX series. So in fact, my own lab has tens of RTX GPUs, right? And NVIDIA RTX 4090 is actually 10 times less expensive than the server-grade counterpart, A100, but it offers 70% of the compute capacity. So in terms of the compute cost effectiveness, in terms of the flops per dollar, it's actually 3.5 times more effective. Okay, so there's no reason not to use this. Okay, so where can we find these GPUs? Well, these GPUs are in Korean PC rooms, right? And do you recognize this T1 Basecamp? And if you do so, you would probably know who is the key figure behind this industry. Who is it? It's Faker from T1, right? So even Faker is the famous esports player who plays a role. He won multiple championships in the world LCK and all the League of Legends championships. Yeah, he's as famous as BTS and Son Heung-min, the soccer player in China. That's what I heard. That's what ChatGPT told me. And even NVIDIA recognized this fact. So if you go to Korean NVIDIA homepage, these are the Korean PC rooms that are GeForce certified. And if you are GeForce certified at the platinum level, if you have more than 100 RTX 4080 GPUs in the same location. Okay? And I looked up the Bureau of Statistics database in Korea, and they're estimated to have around 700K GPUs in Korean PC rooms. Okay? So we have ample supply, and this is fully powered and operational 24/7. So today, let's say you were to buy like 50K GPUs in a server grade, you would immediately run into the power problem, right? You'd have to first locate the power source before even, even being able to buy these GPUs that are not really available on the market for you, right? So, but these GPUs are readily available to you at very low price, and there's actually a Korean company that actually does GPU in the market of GPU spot lending when there's no user in the PC rooms. Okay, so if you go to their site very early in the morning, you have GPUs at very low price, ample GPUs that we can use. So we can have access to these GPUs. Okay, so my vision is to enable AI, large model training and inference, through this inexpensive infrastructure. So it'd be good if we can train very large models or fine-tune large models using a small number of GPUs. We can use it for like research and early development purposes. And we want to be able to use multiple GPUs that are scattered across the WAN for multi-cluster training. And sometimes you want to augment your own on-premise resources with the cloud resources to reduce the cloud bill. All of these amounts to lowering the barrier to AI training and inference, which will accelerate innovation, right? So I want to empower average researchers with the resources they need for their AI research and AI workloads. And enabling this vision actually involves solving two key challenges. The first challenge is that there is this limit in the memory size. So the consumer-grade GPUs have come with 3 to 4 times less memory in terms of the size, and they don't have HBM, so the bandwidth is also lower. So if you were to train large model, then it means that maybe you need more GPUs, right? If you don't do anything with the memory, if you don't apply additional techniques. The second challenge is the limited bandwidth. These resources may be scattered across the WAN, and the typical WAN bandwidth, so we took some measurement from the cloud lab servers, which are cloud testbed for academics. It's connected via internet too. The measurement says the bandwidth is around hundreds of megabits between any two GPUs that are remote. And this is actually 1,000 times slower than NVLink. So we don't have GPU to GPU direct connectivity in this consumer-grade environment. So everything has to go through the CPU and the host NIC, right? So no RDMA. Okay. So yeah, how do we solve these two challenges? So I'm not here to claim that we have completely resolved all the challenges, but I will share you my experience and our journey towards enabling AI through this inexpensive infrastructure. So the first thing we did towards going beyond the memory limit is to focus on an architecture called mixture of experts model. So today's large language models have multiple blocks of transformers. In each transformer block, it consists of an attention layer and a feed-forward layer. In an MOE architecture, we just have multiple feed-forward blocks. And after you pass the tokens to the attention layer, through the gating network, tokens are distributed across different experts. So often one token goes to one or a small number of experts out of many experts. So here we have input tokens in batch. They go through the attention layer, and after going through the gating network, the tokens are distributed across experts. And we call that these experts are sparsely activated. Okay, so regardless of the number of experts, each token goes to only one expert in this example. And one interesting fact about MOE models is that they grow their model size by increasing the number of experts. So we have different model families, MOE small, medium, large, X large. They are derived from llama models. And within the family, you can grow the model size by increasing the number of experts per layer. But interestingly, growing the model size does not increase the required compute capacity of the model. So existing traditional models, as you grow the size of the model, you need more computation. But interestingly, here, the compute requirement stays the same because these experts are sparsely activated. Even if there are many experts, a single token goes to only one or a small number of them. Okay, so this suggests that we may not need that many GPUs if we just consider the computational requirement, right? But this framework, they all load all these model experts onto the GPU. So you need more GPU memory in order to scale the model size. That's because they rely on expert parallelism. Right? You need to have all experts loaded onto the memory. So that's why you need more GPUs. But how can we get away from this limit? So the idea is we use offloading. Okay? So we're going to store all the expert parameters onto the CPU host memory, and we're going to load each expert one at a time for serial processing for the forward phase and the backward phase. Okay? And now that the parameters, the expert parameters are already on the CPU, we're going to also perform expert optimization in the CPU as well. Okay? Let's for now assume that expert optimization works just fine. I'm going to revisit that in the later part of my talk. And let's just focus on this serial processing of experts. We found out that there are two main benefits to serial processing as opposed to expert parallelism. The first is that because we only process one expert at a time, our memory requirement goes down. Okay, so in the remaining GPU memory, we can actually increase the batch size. It turns out that we can increase the batch size by up to 4 times, and that directly delivers us 2 to 3 times the performance improvement. Because increasing the batch size while processing a single expert is better in terms of leveraging the inherent parallelism than loading multiple experts at a time and processing a small number of batch. Because experts are sparsely activated. There's no inherent parallelism in expert parallelism. Although, it suggests that there is some kind of parallelism, right? And then the second benefit is that we can do better load balancing. So the notorious problem in MOE model is that after going through the gating network, the load distribution is determined, but the load is often very imbalanced, especially during the early phase of training, right? So the GPU that has the smallest load always have to wait for all the GPUs to finish their work, right? And this leaves a large amount of GPU time idle. But we can do better GPU load balancing because we do online placement, right? We always have to change load the experts onto the GPU. So let me show the algorithm graphically. So after going through the gating network, the distribution is determined, and we just sort them by the order of load. And then we place each expert in the order of size in like a zigzag fashion. So the combined load of the GPUs are leveled out, right? So there would be a small difference in the load across GPUs. So it's actually much better for load balancing. And in our experiment, it delivers anywhere between 15 to 30% improvement in the actual GPU utilization. So we're about that fast. So sorry to throw you a large table. This shows you for different model family, we increase the number of experts. So as you go down, if you look at the parameter size, it grows. And then we're comparing with different designs, Verisec, Tutel, and Megatron. These are respectively developed by Meta, Microsoft, and NVIDIA. If you look at the small models, we're faster, we're the fastest, right? But if you look at the larger models, existing systems run out of memory, so you can't really run large models. But our system still delivers performance, right? So this is using 4 GPUs, and we can train models with billions of parameters. Okay, so we also can increase the number of experts, meaning that we can grow the model size using the same number of GPUs. Okay, so when we published this paper, Megatron didn't support MOE, so after 1 year, we actually rerun the experiment. It still delivers good, but today's version, the most up-to-date version, actually offloads experts. So I think they're somehow using some of our ideas, okay, but we're still faster than them. Okay, but they're catching up. Okay, so towards this agenda of overcoming the memory limit, we have focused on the mixture of expert setting, and we decoupled model size from the GPU memory by offloading a lot of the experts and optimizer states to the host memory. And we showed that we can scale MOE model training far beyond the GPU memory, and this can be done without sacrificing much performance. Okay? In fact, even the same resource were faster than the state-of-the-art designs. Okay, next I'm going to move to the next agenda. I wish I had done more research on the first agenda, but let me quickly move on to the next one, which is overcoming the network bottleneck limit. So here we're trying to enable model training across the WAN. Right? We want to be able to pool the resources that may be scattered around your own campus, or we want to augment our own on-premise resource with the cloud resources. So ideally, as you add more GPUs, no matter where they are, you would want the aggregate training throughput to increase. But that's not really the case if you run naive data parallelism. The actual throughput goes even lower than using a single GPU, single node setting. Okay, why is that? Because existing distributed training is bottlenecked by the gradient exchange. Okay, so this is a very simple distributed data parallelism setting. After going through the forward and backward phase, gradient is produced, and we have to do all reduce, okay, to update the model. But this gradient exchange phase is bottlenecked because our bandwidth is so low, they have to go through the WAN. Okay, so that leaves a huge amount of time idle in the GPU. Okay, so how much bandwidth do we really need? That depends on the model size. The model size in the x-axis is the same as the gradient size. In the y-axis here, we process the iteration time, how long it takes to produce the gradient. So the slope, x divided by y divided by x, actually is the required bandwidth. And for different models, we plotted the requirement. And these are not even huge models. These are moderate-sized models. Some are even CNN. Some are vision transformer based. And you can see that it's well beyond the WAN bandwidth range in the shaded area. Okay. So if we don't have enough bandwidth, what can we do? We either have to accept that GPU is stalled for training, or we have to resort to asynchronous approach, right? In the asynchronous approach, you run the next iteration without having to wait for the gradient to be all gathered. But this slows down the convergence because your gradient is less accurate because it's stale, right? So in this multi-cluster environment, our goal is to minimize the time to accuracy. That is the time spent in training to reach the desired accuracy level. And like I alluded to, TTA has two components, the iteration time, and it's a product of the iteration time and the convergence time. Iteration time or speed, it means the GPU utilization is how fast can you run the backward and forward pass, and how long you have to wait until the gradient is gathered if you use a synchronous approach. The gradient, the convergence speed reflects how many iterations do you need to reach the target accuracy. Okay, so if you use synchronous approach, your convergence time is fastest. But if you use asynchronous approach, because you don't have to wait until the gradient is gathered, it improves the iteration time, but it comes at the cost of convergence because your gradient is stale. Right? So we employ a number of techniques to improve the iteration time and to optimize the product of the two. So let me first go into the techniques that only affect the iteration speed without affecting the convergence speed, assuming that we use compression. Okay? So here's what existing pipeline looks like when you use a consumer-grade GPU. So after performing forward and backward pass in the GPU, you do compression, you do gradient compression, often gradient sparsification. So for example, you take like top 1% of the gradients, and then you copy it to the CPU for internode gather. And then the result comes back to the GPU, and you run the optimization in the GPU to update the model weights. But you can see this leaves a large amount of GPU time idle, right? So we need to do something about it. The first thing we do is that we observe the gradient always have to be copied to the CPU memory because we don't have GPU to GPU direct connectivity. So why not just do some operations on them in the CPU? For example, we can do gradient compression and optimization in the CPU to remove the clutter from the GPU. But the issue we immediately run into is that CPU-based optimization and compression is 10 times slower than the GPU-based ones. So if you plot the time, the forward pass and backward pass may be comparable to the optimization time in some cases, right? So we need to reduce the optimization time and the compression time. I'll focus on the optimization time for the purpose of this talk. So there are two ways to perform optimization. One is the normal naive dense optimization. Okay, here we start from a compressed gradient, but we decompress it to a dense matrix, and we perform dense matrix operation. Okay? The other way is to apply sparse optimization, which only updates the parameter whose gradient is non-zero using vector instructions. So if you compare the performance, the dense optimization always completes at a fixed time, right? Because it's you run the same amount of operation. But in the sparse optimization, when you compress a lot, when only like 1% of the gradient is non-zero, then you can reduce the optimization time. But 99 compression doesn't result in 99% reduction in the computation time for existing sparse optimizers. Okay? You would ideally, if only 1% of the gradient is non-zero, your optimization time should be reduced to 1/100th. Right? But that's not the case. We have like 18 times room for improvement. And why do we have this issue? The reason is that existing ones do gradient compression. They take top K gradients, but the non-zero gradients are spread all over the place. So if you read by cache line, your I/O is not efficient. And if you try to apply vector instructions, that also is not very efficient, right? So we devise a cache-aware strategy in compression to help with both compression and optimization. So we select the top K cache blocks that has the largest cumulative magnitude in terms of the gradient, right? So our selected gradients are, cache aligned. So our memory I/O becomes more efficient, and vector instructions become more efficient, so that we actually make optimization and compression 17 times faster, almost very close to the ideal case. Okay, so next I'm going to talk about optimizing the time to accuracy as a whole. So even after removing this clutter from the GPU, our GPU stays idle because still we are very bandwidth limited. Okay, so we embrace the fact that we cannot do perfect synchronization. Instead, we adopt stateless. We actually run the next iteration right away before waiting for the gradient to be applied. But we apply the gradient that is generated from iteration n at iteration n plus 2. So we have a bounded stateless of 1. So during the gradient transfer, we execute another iteration. Okay? So this sacrifices some convergence time. We have to run maybe 10-20% more iterations, but our iterations speed is twice as fast. Okay, in the time that we only executed one iteration, we can execute 2 iterations with bounded stateless. So overall, the product of the 2, iteration time and the convergence time, we get net benefit. Oops. Okay, next, we also optimize the factors that affect both the iteration time and the convergence speed. So let me talk about that as well. So here's the effect of the compression ratio on the iteration speed and convergence. If your compression degree is low, then you run into severe network bottleneck because you have lots of data to send. But the quality of the gradient may be faster. So it's good for convergence, but bad for iteration speed. On the other hand, if you compress a lot, it's good for the iteration speed, but your gradient quality is low, so you need more iterations. So it's bad for the convergence time. So you need to optimize the product of the 2, right? So you need to reach a careful point to utilize the trade-off. So similar trade-off happens for the batch size as well. So we actually explicitly model the effect of batching and compression on convergence and iteration speed. So let's try to model iteration speed first. So as you increase the batch size, the iteration speed increases linearly, and after you hit some point, some threshold, it plateaus out. So we can model iteration speed using 2 parameters. Okay, and then because we use one bounded delay of 1 iteration, our compression, our effective size should be less than or equal to the bandwidth times the iteration time. So that's how much we can deliver in 1 iteration time relative to the model size. And this is the relative compression ratio. So if we stay within this constraint, then we can support 1 bounded delay of 1 iteration without making the GPU stall. Next, we also model the convergence speed with respect to gradient compression ratio and the batch size. But the search space is too large, okay? And we don't want the GPU to just spend time on profiling. So we use approximation. In fact, we use the Bayesian optimization that comes up with an approximation of the target function. So it allows us to sample a few points and generate the estimate of the whole entire space. So given a batch size and a compression ratio, we can easily get the convergence by looking up this table, which is output by the Bayesian optimization. So we take this and our controller, we take this offline optimization model, and then our controller online estimates the parameters that affect the GPU throughput, and we estimate the current bandwidth. And using that, we run a numerical analysis, numerical method to minimize the TTA, because we have modeled the 2 factors that affect the TTA. we use what's called a Needler-Med method. It's just a simple numerical method, similar to like a Newton method, right? That works without having to take the gradient. Yeah, even if you don't know the derivative, you can do optimization using Needler-Med method. So every time, periodically, we change the compression ratio and the batch size while adapting to the bandwidth. Okay, so evaluation, we have a 10-node GPU setting. Some are on-premise, some are on the cloud, and we model the WAN bandwidth. We take the trace between two cloud lab clusters, and this is the relative time to accuracy. Compared to the most naive baseline, which is PyTorch DDP, that's the data parallelism default library for PyTorch, we're up to 104 times faster because the baseline is not delivering any performance. So we have this ResNet model and two vision transformer models. Compared to the state-of-the-art baseline, which is BytePS compress, that's from ByteDance. And their existing systems are designed for data centers. And we can, by directly optimizing time to accuracy, we get 2 times the performance improvement. We also measure the cost. Cost-wise, we reduce the cloud payment cost for different models by more than half. And compared to using on-premise only or cloud only, our task runs faster. It takes about 30% less time to get to the desired accuracy. Yeah? So if you're running behind the deadline, you can ask your advisor, oh, let's use this. We can save the cost that we pay to the cloud and save the time to complete the task. So you meet the deadline. Okay, and this is open sourced. Okay, so in StellaTrain, we take a more holistic approach to optimize the factors that affect TTA. We applied a system-aware CPU-based compression, test pipelining, designed for consumer-grade GPUs, and did a direct optimization to minimize the TTA. Okay, so I did one work for each agenda. The first one deals the expert parallelism, or actually uses expert serialism plus pipelining, so to go beyond the memory limit. Okay, so we were able to do that, but still we use A100, right? So we weren't using consumer-grade GPU. Here we use consumer-grade GPU, but we only enable data parallelism over WAN, right? So obviously, there are more work to be done to fully realize the vision and to fully realize the potential that these low-cost infrastructure has. Yeah. So we actually need to achieve both simultaneously to be able to train large models on this consumer-grade infrastructure. Okay. So we already have some implementation that combines the two, but we need further research to enable different types of parallelism and so on. Okay, but instead of going deep, I actually also expanded the front line. So my question was, can we also use consumer-grade GPUs for large model inference? For example, LLM inference. Actually, people say that consumer-grade GPUs are often more cost-effective for LLM serving if you run a very small model, like this 500 million model, right? There's actually from H100 to RTX 3090, there's 50 times difference. So it's 50 times more cost-effective to use consumer-grade GPUs if you run a small model. But of course, consumer-grade GPUs are limited in their resource, so you can't run large models. But we still want the accuracy of a large model, right? So can we combine the power of consumer-grade GPUs and the server-grade GPUs? In other words, can we enable split computing for large model inference? Okay, so previously that has been applied to CNN setting, right? Convolutional models. representative work is neurosurgeon. So you run a few layers at the edge and the rest at the tree, and you send the activations over, right? Can we apply this to an LLM setting? If you do that, you quickly run into a problem. Okay? First, you have to send the entire activation, so it's not really feasible because you're bandwidth constrained. Second, the decoding is autoregressive. So after you get one token, you need to go back and produce another token. So for every token, you incur an additional RTT, right? The RTT is usually larger than one inference time. So your inference, the latency will double or even triple or quadruple. So it's not very practical. Okay? Instead, we adopt speculative decoding. Okay? So let me give a brief primer. So in speculative decoding, we use a small draft model to produce a series of drafts. Okay? So once this small model produces the draft, the target model, the large model, verifies it and corrects the tokens if needed. So we get the accuracy of the target model, and because the target model verifies multiple tokens at the same time, it's also fast. It's good for performance. So it meets the accuracy and performance. So you can run the target, the draft model at the smaller GPU, the consumer grade GPU, and we can do verification at the server. Okay? So this is different from conventional speculative decoding, which does both phases in the server. Okay, so because we only deliver the small amount of tokens to the server, we're now no longer bandwidth limited, but there still is a latency. So to compensate for the latency, instead of waiting for the verification result, the edge GPU actually does proactive drafting. It just drafts more. Okay, so we actually use the state-of-the-art tree-based speculative decoding. So after submitting the tree draft, we don't wait for the verification result come in, but instead we do proactive drafting. So yellow tokens are generated while the verification is going on at the server, and the result comes in, and if it happens to be completely aligned, which means that all tokens are accepted, the longest part of the token is accepted, then we can reuse the yellow parts that have been previously generated. Okay, so this saves the latency as well. Okay, so we did a lot of engineering to make it run more efficiently, the pipelining and all that. And we also adapt to RTT variations and different RTTs in different environment by adjusting the tree depth. Okay, so I'll quickly skip that. Let's go into the evaluation. So we run A100 at the server and RTX 4090 at the edge. And in this particular setting, the RTT was 14 milliseconds. The graph, the x-axis is the inter-token latency, how fast a token is generated. And y-axis is the cost. And we can adjust the batch size at the server. So if you use a batch size of 1, your cost is high, but you get faster latency. If you use larger batch size like 4, the cost is low, but the latency slightly increases. So we have this Pareto front. Our blue one is ours, the spec edge. We have the most frontier, right? And in terms of the cost, we're 2 times more cost effective than existing speculative decoding. And our latency actually improved by 11%, right? So we're faster and we're more cost effective. So this is the demo. Left-hand side is ours. Right-hand side is existing auto-regressive decoding. I thought I'd run out of time, and I fast-forwarded at 17x, so it was pretty quick. But the server throughput is increased by twice compared to auto-regressive approach, and our per token cost is reduced by more than half, which is good, right? So to summarize, my vision is to enable more affordable AI infrastructure to empower average researchers like us. And the key observation is that consumer-grade GPUs often provides a more cost-effective alternative to this expensive HPC world, right? I look up to Faker more than I look up to Jensen Huang. Just kidding. And you need to solve the two challenges simultaneously to achieve that. First is the breaking the memory limit, and the other is the breaking the network bandwidth limit. So in the first work called YesMOE, we were able to scale MOE model training beyond the GPU memory limit by offloading some of the states to the host memory. In the second part of the work, called Stella Train, we enabled data parallelism across the WAN, right, by directly optimizing for time to accuracy. And the very last part of the work, we actually step aside from the memory limit of consumer-grade GPUs by using a small draft model. And then we avoided using large bandwidth by only sending a small number of tokens to the server. And we also overcome the latency by using proactive drafting. So my argument is that by addressing these dual challenges together, we can fully realize the potential of affordable AI infrastructure. And these are the three examples that sort of support this argument. But breaking the two limits together requires more research, like I talked about. Okay, so I invite you to do more research in this area because there are a lot more work to do. I believe I scratched some surface, but even scratching some surface resulted in interesting results. So there are more results, more research to be done in this area. So with that, I would like to conclude my talk. Thank you.
Okay, thank you, Dongsu, for the great talk. Okay, KK has a question.
Thank you.
In your first work, loading the experts seems to take a long time.
Loading the experts, we used most recent PCI because, and then expert computation time and the loading of experts actually time was very similar. So we can efficiently pipeline the two.
So the low-cost GPUs have a very high-speed PCIe.
Yeah. The PCI, the most recent PCI delivers pretty good bandwidth.
Yeah, so this is a very fresh talk.
Thank you.
Yes. So I think we made a correct decision to invest. Okay. So I actually. Hello.
It's okay.
There's a button. Yeah. Or you can use my microphone.
It's okay. Yeah, I still my students here. We're working on this. Actually, I echo your suggestion to work on this. Actually, I have a 160 ITX 3090 GPUs from
Good.
2020. It's been 5 years. We need to upgrade that. Have some restrictions. But I echo your suggestion that I want to do more with. They're still working. Okay?
Right.
So with 160 3090 GPUs, what can I do?
Oh, that's a great question. Yeah, that's a great question. Yeah.
I know you have test with 10 or
Yeah.
GPUs, but
Yeah.
I have 160. I know they are very good, still good. Okay, even I think 4090 has some like metrics not as good as 3090. But
Yeah.
I assume you're very familiar with this.
Right.
And so yeah.
So the challenge, I'll answer your question. The challenge in scaling is twofold. One is that unlike data centers, these the topology is not very symmetric. So the connectivity, so you might have, in one rack, we might have like 10 gigabits per second top of the rack switch. On one end, you might have 1 gigabits per second switch. And their connectivity, if you're going across the room or across campus, they may be very different. So you need to have a hierarchy. So we just enable data parallelism, but to enable like also, you need to also enable pipeline parallelism on top of data parallelism. So this hierarchy has to be set up right for your own topology, which is very not structured, right? And the other part of the challenge is even for data parallelism, the all-gather phase is, you have n different thing is n squared, right? In terms of the bandwidth you need. So that also needs to be, that may be a practical challenge, which actually lowers the actual bandwidth that you can use, but this provides our system works relatively much better when the bandwidth is severely constrained.
Right. So regarding A2, actually we use pretty much 100 gigabit per second network. Regarding A1, so my student, I'm calling my student, he's not here. He's very good at this. We plan to use DRAM to as a backup for
very good. Yeah, we also use SSDs. Yeah, we are.
SSD.
Yeah, one of our sponsors is Samsung, and they make very fast SSDs. Yeah, so we are often even offloaded to SSDs, and they have like CXL interface.
Okay.
Yeah.
So one quick, last quick question. So with this 160, do you have based on your experience, do you have any roughly projection how large models I can handle with them? Presume that we use DRAM or SSDs.
So if you have a cluster that has pretty good connectivity, like 100 gigabits per second, you can enable like pipeline parallelism or even tensor parallelism in that setting, and then do hierarchically apply data parallelism over multiple such clusters. Then you can we will be able to scale.
Okay.
I don't have like first-hand experience on that. Yet.
Okay, good. Thank you.
But please share your experience, or we can work together to scale.
I will invite you to HKUST.
Thank you.
Dumb question. All this runs still on CUDA?
Right, yeah. All this runs still on CUDA, and we use PyTorch.
With his question of a large number of these low-cost GPUs, how difficult is it to deal with lots of heterogeneity?
Heterogeneity is an issue. The compute heterogeneity can be done by, we actually handle this by adjusting the number of batches differently for different GPU models. But the bandwidth heterogeneity is more of a problem. Yeah, so like for data parallelism, we handle that, but for other kinds of parallelism, it's more difficult, yeah.
Okay, we have to stop here and move to the next session. Let's thank Dongsu again. Yeah.
Thank you.
Okay. Good morning, everyone. Welcome to this session named Simulators for the AI Age. In this session, we have 3 papers. The first paper is about network simulation on FPGAs. The presenter is Ran Su. He is a senior researcher at Microsoft Research Azure. His main research areas are cloud and AI infra. Before joining MSIA, Ran received his PhD from Tsinghua University. Okay, please start. Okay, this paper got the Best Student Paper Award. Yeah. Please.
Yeah. Hello, everyone. Thanks for the introduction. So today I'm talking about our paper Miniature, which is a a fast FPGA-based network simulator for large-scale AI network simulation. So for the audience, you may not familiar with the term miniature. So I just show a short video which I took in the Netherlands this year. So actually, I visited a miniature world in Netherlands, and actually, you can see this term that perfectly describe our intention to build such FPGA-based simulator, which we use specialized circuits that can that can run with a minimal overhead to mimic the real behavior of a very large-scale system. Oh, sorry. It seems it's not the latest version. Maybe I can just try my laptop. So sorry for the delay. So actually, I have two versions of the slides, and I use the other version. So sorry.